for the seminar series. Today we're going to have Alex Brand present to us the interfacial transition zone composition and bonding cementitious materials with asphalt-coated parts.
Seems simple, right?
It took a whole time.
All right.
I'm going to tell you about Alex, though. Not everyone knows Alex. He usually works on campus, but I'm glad to have him here. As a researcher in the Department of Civil and Environmental Engineering, he defended his PhD dissertation on August 2015, and will be graduating in December. So it's my good chance to see. Also received his BS in 2010 and made a master's in 2012 from the University of Illinois for engineering. Current research focuses on the microstructural characteristics and bonding between cement-based and recycled aggregates. That's going to be important.
Yeah.
All right. I'm going to let Alex take over.
Thank you everyone for coming. I didn't put PhD after my name, kind of in the grade area. I defended, and all I have to do now is hit submit for my thesis, and then I get a PhD. So it's like I'm Dr. Brand, but sort of. So not officially, not quite yet. So today I'm going to give you guys a brief overview of the main part of what my dissertation was. I'm going to kind of skip over a lot of the fine details and kind of give you more of the results that are important. So if you get confused, you can raise your hand and ask me some clarification because there's a lot of slides I skipped over in my dissertation. I'm sure you guys are going to want to sit through the entire dissertation again. So, what's doing this? No. Let's try this.
There's this power button.
Yeah, it's on. All right, anyway. So we're reclaimed asphalt pavement. I'm sure a lot of you up here know much more about reclaimed asphalt pavement than I do. The whole purpose of my master's and my PhD was using reclaimed asphalt pavement and concrete instead of asphalt. Everything says glass, I'm sure. But the biggest thing is there's just too much of it, and you can't use all of it. You can already see that there's about 100 million tons of it, and we're only using about 70% of it. So what are we going to do with the rest? Now, I'm going to distinguish between wrap and fractionated wrap. Fractionated wrap is more what I was using throughout my research, particularly coarse wrap. That's going to produce something 5/8 to the number 4. That's primarily because the tollway was currently using all of the fine wrap in their new HMA mixes, and so they had stockpiles and stockpiles of coarse wrap. Came to July, figure out what we do with coarse wrap, and started talking concrete, and then where my master's thesis came from. And then I changed to a lot of other science with regards to wrap, and now for this work we're figuring out, more properties and why things decrease. So if you look at the literature, there's only about 20 or so studies out there. You can see they all pretty much unanimously agree that wrap is going to decrease your strength and modulus. So the biggest question is, why does that happen? And when can we prevent that from happening? Can we somehow, what's going on kind of at the microstructural level that we can change such that we don't get a decrease, or at least reduce the magnitude of the decrease? Instead of a 20% reduction, we could say 10% reduction. So that was the goal of kind of the dissertation here. And you can see that pretty much with strength, we're seeing maybe about 20 to 50% reduction in strength when you add 50% coarse wrap. So that's a pretty significant reduction in strength. So again, how can we change that? So for my master's, we kind of looked at the dynamic modulus, figured out that it wasn't the coating or the stiffness that was affecting it. Therefore, we kind of concluded it must be something going on at the actual interface. In particular, in concrete, there's something called the Interfacial Transition Zone, the ITZ. This is the bulk of everything I'll be talking about today. So for those of you who aren't familiar with what this is, when you first cast concrete, you kind of have fresh cement base and rock. So as cement base hits those rocks, you kind of get what's called a wall effect. So those cement grains cannot pack effectively against the aggregate surface. Picture like tennis balls. If you have them in the middle of the room, they can all form nicely compact together. At a wall, they can't pack as densely, right? So that's why you kind of get this interfacial transition on the wall effect. So you have less density, more porosity, less custom silicate hydrate combining these cement and concrete. And all in all, it's just the weaker phase of the concrete. Thus, it's considered a weak link. So if you look at the literature, we figure out that there are pretty much three main causes of why the ITZ is weakness, weakening of concrete failure. So one, it's much more porous, so it allows for easier crack propagation, it's a lower compliant phase, it's a lower modulus. There's large age crystals that are preferentially oriented, so as a crack comes along and hits that plane, you can easily go right along that CAD plane. And then you actually have the actual bond, so like say the chemical interaction or the physical interaction, and the actual interface between asphalt and cement. So basically my dissertation, or at least chapters 2 and 3, chapters 4, 5, and 6 we don't get into, because those will take another couple hours presentations. But 2 and 3 we'll focus on today, and that's systematically going through, looking at concrete with wrap, and looking at these three components, what's different with these three components with wrap, and how can we change it. So we'll start with purely looking at the interfacial transition zone. So pretty much, how is the wrap affecting the interfacial transition zone? Is the porosity, is this calcium hydroxide different? And we add other materials to try and improve it. So what we used is compositional backscatter electron microscopy. Everyone's heard of electron microscope, right? Anyone not familiar with electron microscope? So pretty much an electron microscope, instead of using light like you would in a normal microscope, you're using electrons. And then you have the detector things and digitized image and whatnot. But pretty much if these electrons come in, there's your primary beam of electrons that hits the surface. Some electrons bounce off the surface, those are called secondary, SE. So that's the analogous to in a light microscope, light coming in, hitting the surface and coming into your eyes. That's analogous to that. What we're using instead what's called backscatter electrons, BSE. So in that one, the electrons come in with such energy they come inside, they go inside the material, bounce around a bit, and then get ejected. So these backscatter electrons are a function of the atomic number. So it gives you information of the composition of material. So pretty much we'll see that high atomic numbers like iron are bright, low atomic numbers like carbon are kind of dark. That's kind of what we see here. Here, for example, is normal concrete with virgin. This is dolomite. So everything comes in as grayscale. So unhydrated cement, UH, appears bright. So unhydrated cement has a lot of iron, aluminum, things like that. So that's bright waste. Calcium hydroxide is kind of an intermediate light gray. Porosity, so we fill all the pores in of your sample with epoxy. That epoxy is carbon-based, so those are black. Similarly, asphalt, also carbon-based, appears black. Now, sample preparation is the biggest headache you will ever have to face. If anyone ever wants to get into this, once you figure it out, yeah, it's easy, but it takes many, many months of trying to get it to work. So what you basically have to do is cut a thin sample, somehow get the epoxy to penetrate through your entire sample, and then you polish it down all the way down to sub-micron fineness. And that just, we needed that fine to get a good compositional contrast in a plane. So I have some samples of people want to love, but once you have asphalt, that makes things even worse. So already like trying to just make cement samples is a problem. The asphalt is a problem because a lot of the preparation methods in the literature use harsh solvents. You know, ethanol, acetone, things that we can't really use with asphalt because it'll dissolve. So we had to kind of come up with alternative methods because of the asphalt. So in the end, we made it work, we got it to work. So here, for example, is a 1 PA image. You know, so instead we have kind of an asphalt mastic in the wrap that's kind of coating the aggregates. You can kind of see it's asphalt with, you know, bits and pieces of rock in there. And you can see the ITZ at one day is very clear. You guys can see, I can see a little bit clearer, maybe not so much. You can kind of see this, here we have kind of interface. And you see this whole region nearest appears a lot darker. It's a much higher porosity. So you can almost visibly see the ITZ in an early sample. And everything else is kind of the bulk paste. So what you have to do is first, it's in grayscale. So you have to threshold that grayscale image to pull out each of those phases. In the literature, you can pretty much figure out what's unhydrated cement, it's bright white. You can figure out the CH, it's kind of lighter gray. Everything else kind of just fits in this hydration products. So that's things like calcium silicate hydrate, etringite, monosulfoluminate. You can't exactly call it anything. Porosity doesn't exactly have a peak, but there's nothing in the literature we can use to pull out porosity. But basically using this idea that for each image, you can threshold your phases. And I'm kind of skipping over a lot of how we get all of that. If you want more details, I can tell you later. But pretty much we have our thresholded image. So now there's 4 colors. So pretty much showing us our unhydrated cement, calcium hydroxide, darker gray is everything else, and then black is porosity. You create a binary map, which this is highlighting, everything white is highlighting just the pores. And then we apply this thing called the Euclidean distance map to figure out the distance distribution of this phase with regard to this interface. That's what we have down here. So pretty much we take 50 or so images, run this algorithm, and then you get these averages. And that's what we come in here. So pretty much we looked at a number of different wrap sources, and we even added one with silicon fume. Silicon fume is known to kind of improve your ITZ. You want to see if that will help. And then we looked at these samples at different ages, see how the ITZ changes. So now here we have at one day, so each of these, so we have porosity, unhydrated cement, and calcium hydroxide. Each of these lines is the average of 50 to 60 or so images. So we can pretty much see that porosity, they're all following a pretty similar trend. You know, just because we only use 50 to 60 images, if we did like 4,000 images, everything should theoretically average out to be the exact same line. But you know, we're trying to get a representation of the samples just by getting 50 to 60 images. But in the end, there's not a whole lot different between dolomite versus wrap. We'll skip over. So since this is not different, we can see that in the literature, if we look at one-day ages, it's not really, wrap doesn't really affect the concrete strength of one day. And that kind of agrees because the idea just isn't developed enough to cause any issues. If we look at 28 days now, we can clearly see porosity. So for dolomite, porosity drops off immediately and then kind of just levels out. Whereas with wrap, it's much higher porosity content, and it's a much longer time before it kind of levels out. So that's showing us that the wrap is having a larger, more porous ITZ. Unhydrated cement, again, relatively similar. The other thing to note is calcium hydroxide. Very large calcium hydroxide. Calcium hydroxide likes to grow against carbonate minerals like dolomite, but it seems not like to grow against asphalt as much. So that's something we needed to look into as well. So pretty much the biggest thing to note here is we have a very large porous ITZ because of the wrap. Now when we add silicon fume is a very tiny particle, like 100 times smaller than cement. So you can add this nice filler effect. It's very dense microstructure. And then over time it reacts polysonically, and you kind of just overall get more CSH, much denser microstructure. So we can see that adding silicon fume, okay, that helps us a little bit, just because of the filler effect. But in the end, even at 28 days, okay, we have less porosity, but really it's not getting us to where dolomite is, for example. So now here we have the dolomite again on the bottom. This is with silicon fume, and then without silicon fume. So we can see that silicon fume is helping us a little bit, but not to the point where it's as good as dolomite. And this explains exactly why adding silicon fume to concrete with wrap has not shown to have any effect. So here in this study, they had concrete with coarse wrap, no silicon fume, 10% to 20%, and you can see it's barely any difference in the bulk strength. So in the end, silicon fume is very expensive. It's not worth it to add silicon fume to concrete with wrap. So again, why is this? Why is this going on? And it's because of this. We still have this large porosity. Trying to estimate the CSH content. Again, we can see that there's kind of less CSH immediately in the interface because of the wrap. So again, there's just not as good of a binding phase, in that ITZ. Skip over a lot of the details with the CH size and morphology. We just did more image processing to figure out, how much CH is in the sample, how much of it is, in a certain distance of the interface, things like that, particle size. So in the end, we found that the CH might be slightly smaller overall, on average, as opposed to dolomites. So perhaps the asphalt is somehow poisoning the CH or stealing the CH, something's going on potentially. We get into that a lot more in the next section. So, if you recall, these are the three things we need to look at. So this chapter 2, we wanted to see if there's a difference in porosity and CH because of the wrap. So that porosity, yes, we clearly see a much larger FTZ with more pores. The CH, not really that much of a difference. They might be slightly smaller particles, but in the end, the effect is not the bulk reduction, the 50% reduction in strength we're seeing. We can't attribute that to the CH. The porosity, maybe. All right, so now we still have to look at part 3 there. What is the actual cement asphalt bond? How is that, what's going on there? So we want to kind of look at what is the interfacial energy, what is that interfacial bond, how's it going, and then can we change it, can we improve it? So let's first talk a little bit asphalt chemistry and composition. Everyone probably knows it's just large hydrocarbon molecules. You know, they contain carbonyl sulfoxide groups as carbon-oxygen bonds, sulfur-oxygen bonds. And we know that oxidizing them will further increase those carbonyl sulfoxide groups, in particular carboxylic acid groups with severe oxidation. That's what number 1 forms. But the literature tells us that calcium might be associating with those carbonyl groups. So perhaps if we further oxidize the asphalt, maybe we'll get a better bond. So that's the basis of the hypothesis for chapter 3 in terms of where we took it. The other thing we kind of looked at is, you know, you can toss in other materials, other chemicals, and try to improve that bond. We already showed silicon did not do too much, but what about, you know, other agents? So polymer modification, polyvinyl, all of those in the literature have shown potential bond improvement with virgin areas. No one's looked at it with wrap. So we brought it to wrap. So pretty much based on the literature, we kind of found a whole bunch of different things on how we can rapidly oxidize the asphalt with various chemicals, mostly acids, or maybe possibly from bonding through these chemical additives. So let's skip over a little bit here in terms of, we just did preliminary, you know, proof of concept tests, and found that the dynamic modulus, this is the resonance frequency dynamic modulus, not the dynamic modulus is right here. So based on resonance frequency, our dynamic modulus appears to be increasing, and actually a statistical increase with some of the treatments. So that's kind of telling us that, okay, we are possibly oxidizing the wrap, the asphalt on the wrap. We're possibly getting some sort of bond improvement, but certainly it's not evidence. So the next thing we looked at is to try and quantify the actual carbonyl sulfoxide groups. So in that method, we use Fourier transform infrared spectroscopy, FTIR. That pretty much, but once you shine infrared light on a sample, you kind of excite these various bonds. So for example, with the next slide, so here's the an FTIR spectrum, and we kind of, so at this frequency, we excited the CH stretching. So it's CH bonds are doing stretching, or you have bending ones, and all sorts of ones. So basically, we can pull out our carbonyl and sulfoxide groups, and kind of by normalizing over the whole area, we can compute what was on the previous slide, these spectroscopic indices. In particular, we're interested in the carbonyl sulfoxide groups. So quickly, we're looking at those results again. I'm kind of skipping over some stuff. We showed that, yes, we are getting more oxidation with a number of these treatments. So here's our virgin asphalt, that red line is kind of the baseline. So certain things, so hydrochloric acid, chromic acid, phosphoric acid, all those are kind of increasing our oxidation. Okay, so now we know that if we treat the wrap, we're getting some sort of bond improvement with the dynamic modulus. We know from this that, okay, we're getting some sort of increase with our carbonyl sulfoxide groups. We are getting oxidation, but again, what does this tell us? So let's actually now quantify the actual bond. And that's with our friend surface free energy, which is the equipment we have in the lab next door here. So, is anyone here running that test? Anyone? Okay, one person. So some people are familiar with it. So pretty much you drop a liquid on a surface, and it's either going to have high wettability or low wettability. So picture like Teflon or, let's say, wood. So something that has a good repel or not. So pretty much based on this contact angle, bring that as components of the various surface energies. So we have the liquid energy, the solid energy, and then the interface energy, the two. So from a classical equation, so our work of adhesion, and that equation from the previous slide, we combine those, we have this Young-Dupré equation, and then we can use the VOCG theory, which you guys probably can't see, but it's a pretty good theory. No, don't read that though. The guy's name is Good, so it's a good theory. All right. Anyway, that appears to have gotten cut off. I'm sorry. I didn't realize that cut off. Anyways, you have this equation that basically splits now your work of adhesion into kind of these polar or non-polar van der Waals forces and your polar groups, Lewis S and Lewis base. So it's pretty easy. You have this equation. You measure the contact angle for 3 different liquids of known values. So now you have 3 equations, 3 unknowns, and you solve it. And that way, from there, you can then compute kind of your surface energy of your surface. This is the equipment we have next door. You can just drop a liquid, measure it, fix the contact angle, so on and so forth. And then from there, you can compute other things that pretty much this is the energy of adhesion, work of adhesion, energy of cohesion, also the interfacial energy. So we go through and compute all these different things. So the first thing we did is really just look at the total surface free energy. And here we just kind of took a PTC 422 and treated it with these various treatments for 15 minutes. And we can see even with the 15-minute treatment, we're increasing the total surface free energy. And then we also measured hydrogen and taste. So now if we go through and compute these free energies of adhesion, or if you want to think of it as work of adhesion is just negative this, I'd like easier to think of it. So it's either, so more negative is better, it's more attractive. Or if you think of it as work, it'd be the higher number is better because it takes more work to separate them. But pretty much what this is showing us is between asphalt and cement paste, once we treat it, we have much higher interfacial energies and much higher work of adhesion energies. We're getting as much as 200% increases in that interfacial energy. So this is telling us that with this chemical treatment, this chemical oxidation, we're getting kind of a stronger bonding energy to that interface. However, here's the curious thing. The work of cohesion of the asphalt itself is 50. But the work of adhesion with cement is 65. So as you have a failure crack coming through here, it's going to go through the lowest energy state, which would be through cohesion rather than adhesion. So this is kind of telling us that, great, we improved this energy of adhesion, but it doesn't matter because the cracks probably still just go through the asphalt as a cohesion, because it's a lower energy state. And you can kind of see that with some images. I brought some samples too. This is a sample that kind of got the split tension, so it kind of got split into 2 pieces. So you can kind of see the asphalt pieces on either side. A lot of these cracks, you can clearly see, just went through the asphalt, rather than this one did the asphalt and the crack went through the aggregate. So that kind of supports our empirical evidence that, yeah, we're seeing failure lanes going through the asphalt rather than through the interface of the ITC. So then, I'm skipping over some more tests we ran, but then of course we also sort of look at the ITC. Are these treatments, so these treatments are affecting the actual asphalt, but is it affecting then the ITZ, that area of 50 microns, extending into the matrix? In the end, no. So basically we treat the asphalt, it's improving our work of adhesion, our interfacial energy between cement paste and asphalt, but it's not affecting our ITC. So the ITC is still pretty much just as porous, just as little CSH, things like that. So there's minimal benefits, it seems so far, for these treatments. And then again, looking at kind of the CH particle size, calcium hydroxide, again, I'm skipping over what we did in that. We can kind of see that with these treatments, our average particle size is decreasing. Again, suggesting, maybe something's going on with the asphalt. So if we look at the literature, these are more studies kind of from Western Research Institute and things, kind of looking at how does lime and asphalt interact and things like that. And then kind of found that, yeah, CH does kind of react or associate with certain functional groups in the asphalt, particularly carboxylic acid groups. So that's kind of suggesting that, hey, maybe we're adding more carbonyl sulfide groups to the asphalt now. We're getting smaller CH particle sizes, so maybe it's kind of skewing away some of that calcium at the interface. That's kind of all just speculation. A lot more studies needed, but it's suggesting that something is going on. So in the end, back to our big three here. This one we looked at here was kind of the interface. So what's going on? Is it affecting the strength of modulus? And yeah, absolutely. So since as cement ages, you have it maturing, it's gaining strength, it's hydrating. So great, now your matrix is gaining strength, your ITZ is gaining strength. But who cares? Because the crack is going to go just through the asphalt. Thus, we still have these reductions in strength. So, to summarize a lot of this stuff we've been talking about, we can see that at one day, there's not much asphalt in the concrete affecting the ITZ very much. And that's why we don't see much effect on strength in early ages. Later ages, yes, big effect. So we're seeing a much larger porous ITZ, less calcium silicate hydrate, less calcium hydroxide, but similar unhydrated cement, similar calcium hydroxide morphology. So the kind of the shape and the orientation of the calcium hydroxide particles are similar. It's the size that might be affected, but we need more data on that to confirm that. And again, silicon fume, even though we know it to improve the ITZ, is having a minimal effect on concrete with RAP. We can oxidize the RAP, we can improve these carbonyl sulfoxide groups, we can improve the work of adhesion, but based on the surface energy, we're still going to have an asphalt cohesion failure rather than an adhesion or an IGT cohesion failure. So pretty much overall, all this data suggests that the reason we're getting that reduction in strength when we add RAP concrete is one, with a much larger porous ITZ, so it's allowing for easier crack initiation and also propagation as the cracks go along. So therefore, we're reducing the bolt strength a bit. It's also lower modulus space, so it's more porous, so it's more compliant, and now it's larger. And thus, overall, the bolt modulus of the concrete is being reduced. And we actually also, my thesis I didn't present here, we did some models, and yes, confirmed that it is affecting the modulus that much. And then finally, we have kind of this cohesive failure of the asphalt. And again, that's kind of reducing your bolt strength, even though your cement is gaining strength over time, crack section is going into the asphalt. So, with that, a lot of information, I kind of skipped a lot of details, but if you have any questions, any clarifications, anything else you want to know, if you want my 500-page thesis, I can provide that to you. So yeah, any questions? Yes.
Can you refresh me on the reduction in 28-day strength was for the different?
So our functional strength is reducing about 20%, compressive strength maybe about 30%, and split tensile strength about 50% when we're adding 50% RAP. Now currently the tollway is using RAP and concrete for the two-lip paving, but they're only adding say 10-15% RAP. So the ultimate, bulk reduction of strength is, it's there, but it's not significant. Anything else? All right, let's continue with the question.
So, go ahead. So when you run the actual bonding test on the binder and navigate, so did you use the cloud binder from the RAP, or did you use that version binder?
We use version binder.
But actually, you blend the RAP into the concrete, right?
Right.
But supposedly the RAP is actually the RAP binder.
Right. No, absolutely. But we wanted to kind of look at a perfect scenario where where we're controlling kind of how much carbon. So already your asphalt on the wrap probably already is pretty oxidized. But we wanted to see if we have just virgin binder, how much are we increasing that carbonyl sulfoxide group by treating it with chemicals. So we wanted kind of the best case scenario. But yes, we should look also at the extracted asphalt. Yeah. No, it would be. But of course, any asphalt we use in a different grade, polymerized, all those also affect things.
Yeah, I had a question about the two-lift concrete, the 2016. That's relatively new, right?
Yeah.
Like, are they seeing the decade or something? Within the decade or even?
Yeah, so they're building it right now.
Right.
So right now it's a 50-year design like pavement. So it's a 13-inch, 13.5-inch concrete pavement. The bottom lift, I think, is 8 or 9 inches of concrete with wrap. Top lift is virgin engineered concrete, much higher quality aggregates like that.
So have they seen, or have they seen like the performance, or are they happy with it, or is it too soon to tell?
It's too soon to tell, but there have been experimental pavements. So Kansas built a two-lift wrap in 1997, and the data and my thesis on that, but it's basically, so the two-lift pavement, bottom lift at 15% wrap, and right now joint vaulting and joint LTE is the same as the control section. So even after what it would have had, almost 20 years, it's performing just the same as control. So yeah, it can perform well. And another tip from my thesis, we looked at the actual flexural load capacity of full-scale concrete slabs, which we did in the soil bed next door, and basically found that the wrap is not affecting the total flexural capacity of the slab. So you're getting reduction in strength, but you also have to look at the fracture properties. Fracture properties are the same, relatively. So kind of the total slab performance is comparable to normal concrete. Anything else? All right.